inference for quantitative data, specifically for mean. All right, we're going to start off with confidence intervals for means. Just like we did confidence intervals for proportions, now we're starting with confidence intervals for mean. In the past, we've used z-scores to approximate the probabilities for finding a mean. However, this hinges on the idea that we know mu, the mean, and sigma, the population standard deviation. When we're trying to find confidence intervals for an unknown mean, we're probably not going to know the population standard deviation either. If we don't know the population's mean, we're not going to know the population standard deviation. It only makes sense. We can substitute a sample standard deviation in place for the population standard deviation, but that gives us a completely new statistic. That statistic is the t-statistic. For normal distributions, we had a z-statistic. For t-distributions, we will have the t-statistic. The t-statistic looks a lot like the z-statistic, or a z-score, if you will. You still take the sample mean minus the population mean, and instead of dividing it by the population standard deviation over the square root of n, you divide it by the sample standard deviation over the square root of n. The t-statistic has what we refer to as degrees of freedom that are equal to whatever the sample size is minus 1. So when the population isn't normal, it's going to have, the t-statistic will have approximately a t sub n minus 1 distribution if the sample size is large enough. But what is a t-distribution? Well, a t-distribution is very similar to a normal distribution. It just looks a little bit different. So when we standardize based on the sample standard deviation rather than the population standard deviation, it's going to take a slightly different shape. It's still symmetric with a single peak at the mean. However, it's going to have a lot more area in the tails. So basically the spread is wider. How much wider depends on how large the sample size is, much like everything else. So each different sample size is going to have a different degree of freedom and therefore a different distribution. So every single t-distribution is slightly different. How different is up for debate, but we're able to get pretty precise with our calculations. When you compare the shapes on top of each other, you see that the t-distribution for low degrees of freedom, like 2, has a lot more area in the tails and a lot less area in the middle where the peak is. For 9 degrees of freedom, it gets closer and closer to a standard normal distribution. And then, of course, the standard normal distribution has very little area in the tails and a lot more in the middle. So, however high the degrees of freedom are, the closer to normal it's going to be. But since we have the t-distribution, and the whole point of this is to be as precise as possible, we use the t-distribution whenever it's appropriate. Now, using the table to figure out what t is, or what the critical t is. So just like with z-scores, you can use the degrees of freedom to figure out what your t-score is going to be, right? So what critical t you're going to use from the table should be used when you're constructing a confidence interval for the population mean. And here's an example. So let's say we want to make a 90% confidence interval from a random sample of 48 observations. What are the degrees of freedom? And is it directional or non-directional? Now, confidence intervals are always going to be non-directional, which means it's going to be two-tailed. Now, the reason we point that out is because usually with these tables, they give us two values, one for when it's one-tailed, one for when it's two-tailed, and it's important we know which one we're looking at. So, we want 90% confidence for a random sample of 48 observations. Since our sample size is 48, our degrees of freedom is going to be 47. Remember, degrees of freedom was equal to n minus 1. So we need to take 48 minus 1 is 47. So we're looking for, in the table, 90% confidence for 47 degrees of freedom. So here's our t-table. We have the cumulative probabilities up on the top row, and then how much should be left over if you're doing a one-tailed test versus a two-tailed test down below. So since we're doing a confidence interval, it's comparable to having a two-tailed test, right? So you have a 90% confidence interval, so you'd have 10% between the two tails. So we're looking at 0.10, and our degrees of freedom were 48. So we scroll down in this table until over on the left-hand side we find a 48. And we don't actually have one. Our table goes from 40 to 60. So what we need to do is we need to play it safe, as we tend to do in this class. So the conservative safe model would say to go ahead and round down your degrees of freedom. Don't assume you have more in your sample than you actually do. So we're going to use the t-statistic for 40 rather than the next one we have on our list, which is 60. Now, some t-distribution tables that you can find online will have more options. There's some that will give all the way up to 50, but this one that I linked in doesn't, and that's okay because we'll just play it safe and use the critical T of 1.684. So the critical T for 48 degrees of freedom / 40 degrees of freedom for a 90% confidence interval would be 1.684. I don't expect you guys to memorize these because every single degree of freedom has a different value, so don't plan on trying to do that, right? So here's the critical Z's. Now, once you've found the critical T, the format for calculating a confidence interval is basically the same as it was for proportions. You have your point estimate, which in this case is x bar, the sample mean, and it's plus or minus the critical T times the standard error. Now, for sample means, the standard error is actually a lot less complicated than it was for proportions. You just take the sample standard deviation, which will generally be given to you in the problem, and you divide it by the square root of n, which will also be given to you in the problem. Otherwise, you couldn't do any of this. So when you put it all together, confidence interval for the population mean is equal to x bar plus or minus the critical T times sample standard deviation over square root of n, where, of course, critical value for the distribution with whatever confidence level you're looking for. In our case, it was 1.684. Now, the conditions for constructing confidence interval are important just like they were for proportions, and we need to make sure those conditions are met every time. In this case, the conditions are pretty much the same as they were before with some minor tweaks, right? So first, we need to make sure the data comes from a randomized experiment. That's going to be a theme throughout the rest. We need to make sure that our sample is less than or equal to 1/10 of the entire population, or 10% of the entire population. This is not that we have X many successes in our sample size. It just means that our sample has to be less than blank, less than 10% of our blank population. Now, the large counts rule changes just a little bit compared to what we're used to, because there's some caveats, there's some workarounds, right? So if the population is from a normal distribution, or if the sample size is large enough, basically n is greater than or equal to 30, then you can go ahead and proceed. Your large counts rule is met. If, big if, the population distribution has an unknown shape, then what you have to do, and the sample size is less than 30, then you have to graph it to make sure it looks approximately normal. If it shows any skewness, then you can't do it. If it doesn't, if it looks approximately normal, then you can go ahead and use a t-distribution even though your sample size is less than 30. If you'll notice, the degrees of freedom go all the way down to 1. So realistically, you could do a t-test, you can make a confidence interval using a sample of size 2, because n minus 1, if it's for degrees of freedom, your sample size could be as low as 2. You can't do 1 for 0, but that just means you have the 1 statistic, right? So you can realistically do something with a very, very small sample size if you know it's from a normal distribution to begin with. It doesn't necessarily have to be a sample size over 30. So let's go ahead and run through an example, right? Let's say environmentalists, government officials, and vehicle manufacturers are all interested in studying the auto exhaust emissions produced by motor vehicles. The major pollutants in auto exhaust from gas engines are hydrocarbons, carbon monoxide, and nitrogen oxides, or NOx for short. Researchers collected data on the NOx in grams per mile units for a random sample of 40 light-duty engines for the same type. The mean NOx reading was 1.2675, and the standard deviation was 0.3332. Construct and interpret a 95% confidence interval for the mean amount of NOx emitted by light-duty engines. So we have all of our important information here. The sample mean was 1.6275. Sample standard deviation was 0.3332. Sample size was 40. Confidence level was 95%. And we're trying to find a confidence interval for the population mean. I'm going to do this one by hand first, and then I'm going to not ever do it by hand ever again. So first, if we're going to do it by hand, we need to know the degrees of freedom, right? It's a t-distribution based on degrees of freedom. If n is 40, then the degrees of freedom equals 39. It's n minus 1. So in this case, it's 39. So what we need to do to find the critical t is go to our t-table, find 39 degrees of freedom at a 95% confidence level. So using that same table, we see for two tails, a 95% level would be in this column. We scroll down until we see 39 on the left. We see that we don't have a 39. No, we cannot round up to 40. You never want to assume you have more in your sample than you do. You always should be conservative. In this case, we're going to use the 30 instead of 40. So we're going to use a critical T of 0.204. And there we go. So remember, the formula is x bar plus or minus the critical T times the sample standard deviation over the square root of n. So that's what we're putting in the calculator. I'm still going to use the calculator a little bit. I'm not going to do the square root of 40 inside parentheses by hand, right? So now I know this is the TI that, we said that we can't use, but you can do the same thing in any scientific calculator, any four-function calculator realistically. So you can use Desmos to do the same calculation. So like I was saying, 1.6275. First we're going to do plus, so we'll get the upper bound first. Okay, so there's the upper bound, 1.735. Confidence interval, 7.5 is the upper bound. And lower bound, literally typing the same thing, but with a minus sign there. There's the lower bound, 1.51, or 1.5. And there we go. There is the 95% or 95% confidence interval. We are 95% confident that the true mean NOx level for the trucks is between 1.52 and 1.35 grams per mile, and that's calculating confidence interval. Now, if you're using the calculator, as I recommend you do, it's quite a bit faster. So first, remember the name of the class you're in. You're making a confidence interval, and we're making a t interval, right? We're going to input statistics because they did not give us the raw data, thankfully. The sample mean was 1.6275. Sample standard deviation was 0.3332. We had 40 in our sample, and our confidence level is 0.95. And this confidence interval is going to be a little bit more precise, we see, because we're able to use actual 39 degrees of freedom instead of rounding down to 40. So we see that this interval is between 1.52 and 1.73. So I wasn't too far off. Yeah, I mean, I was just underneath, right? Did pretty good with rounding. Now, last point of order, choosing a sample size. So just like before, when we're making confidence intervals, a lot of times we'll be asked to select a sample size that will give us a confidence interval that has got a small, significantly small margin of error, right? So just like before, we can reverse engineer the margin of error in order to get an n that's appropriate. The trouble is that the critical T depends on n, right? So before, what we had to do was we would look at the sample size to determine which critical T we're going to use. Now we don't have that option, right? This is okay because the normal table will be narrower. Therefore, any Z that we use with a comparable sample size will be safer than using a specific T, right? So what we can do instead is swap in a Z for a T, and the rest of the formula is actually a lot easier. So critical T, if we want to get a sample size under a certain margin of error, the margin of error is found by critical T times standard deviation divided by the square root of n, and that's got to be less than or equal to the margin of error. Therefore, the formula for calculating n, or the smallest necessary n, will be n equals z squared times sigma squared over the margin of error squared. I'll run through several examples of how to calculate that in class, but I'm not going to right now. And that is everything there is to know about calculating confidence intervals for means. I hope this was helpful.